All right. Okay, so good morning, everyone. As usual, I hope you are doing very well. I see that we are all starting to be confined again, so I hope it will go properly with everyone. Again, feel free to contact me if you get lost or if there is any problem with this course, or more generally with the master, of course. I will do the relay. So today we are dealing with tutorial number 4. Normally you found in the Dropbox all the videos for the previous tutorials. Please watch them again if you need to come back to those ideas. And for today, there are 2 things that we will discuss. The article by Gabe and Gareth that you have in front of you, and the tutorial associated to that. But before doing so, I would like to introduce you the book of the day. So the book of the day is this one. It's a book that is called Scaling Concept in Polymer Physics. I don't know if you see it properly here, the title. Okay, so it's a very gray-like book, as you can see. It's not very thick as well. I mean, this is really the polymer physics book. It's more complicated to read than the one I presented to you last time by Rubinstein and Colby, which has more first-level approach of polymers. This is dense. It's pretty dense. You have ongoing ideas of polymer physics inside. You have statistical field theory. So it's a very elegant book. If you start to know a bit the field, you will learn a lot from it, but it takes some time to digest it, okay? And it has been written by Pierre-Gilles Degene. Pierre-Gilles Degene had this particular style of working 5 years on a topic and then writing a book that is now each time, for each of those books, a very fundamental piece of bibliography. So he did that for liquid crystals, he did that for superconductivity, also for droplets and bubbles and weighting, and this one is for polymer physics. So it's very impressive, and everyone uses it in this field. All right, so today we would like to talk about this article by Gabe and Gareth. You remember that we were first dealing with ideal polymer chains with no interactions. Then we introduced the interaction with between monomers, but also between the monomers and the solvent molecules. And by doing so, we were realizing that everything could be recast into a simple parameter, which was the Flory parameter, or if you wish, if you prefer, the excluded volume. So this parameter characterizes all the interactions in a sense, and the properties of the chain were modified on the statistical aspect with respect to the ideal chain. In particular, the chain was more swollen, larger extent, when this parameter is positive, when the interaction between the objects is typically repulsive, R-sphere repulsion. So in this tutorial, we would like to deal with an interesting idea. If you remember, we identified that the interactions in the polymer problem tend to vanish, to go to 0, when we reach a special dimension of space, which is dimension 4. In dimension 4, the interaction don't matter anymore, and we recovered an ideal chain behavior, despite the fact that the interaction was finite in a sense. You branch finite interaction between the monomers, but due to the large dimensions, if you wish, those interactions didn't matter anymore, and we ended up with a Gaussian ideal statistics. So there is an interesting idea that came in the literature, that is, just place yourself at 4 dimensions and then do an expansion in the dimension towards the 3rd dimension, okay? It might sound weird, but it's a classical technique in field theory. And by doing so, you will reintroduce progressively the interactions. So if you want, it's a kind of perturbative analysis, but performed on the dimension. And this was proposed in this article based on renormalization ideas, and we will try to digest that and give you the main feature of this technique. Okay, so I guess you are not all familiar with renormalization, so that is why we will go slowly with this. All right, so please take the tutorial, which is the next, this one. Okay, it's called renormalization along a macromolecule in a dimension close to 4. Take this one, and I will share my whiteboard, and we will go to the whiteboard now. Okay. All right. Prepare so that we have proper space to chat. Okay. All right, so we are dealing here with the following problem. We have n monomers. So as usual, the drawing is the following. We have a polymer chain that has a certain number of units, n, which is very big compared to 1. It's tending to infinity typically. This chain is in fact made of monomers. I only draw one here, for instance. But there are plenty of those of a certain size A, which is nanometric. We already went through this. We are living in a world where the dimension is D for now, and it can be a priori anything. And we are branching interactions between monomers. For instance, these guys are talking to each other with an interaction that is described by the Flory parameter, Xi, that we introduced in the last tutorial. Remember, we were defining equivalently the excluded volume parameter, which was the volume of the R sphere of a monomer, and there was 1 minus 2 Xi. So in fact, defining V or Xi is equivalent, and we might even put it in a normalized fashion, a dimensionless fashion, so that we have 1 minus 2 Xi. And this we will call it U. U is the coupling constant of our field problem, if you wish. Okay, it's a dimensionless coupling constant. Okay, so this is the problem we want to do, and what we want to do, in fact, is to use the renormalization technique. Sorry, and the idea is the following: is that we will group together a certain number of monomers and group them in bigger units like that. Okay. Assume I can do that on all the chain. Okay, so I just say, for instance, I have 1,000 monomers in the real chain, but I will group them 3 by 3. So I will do little bags with 3 monomers, and then I will recompute the interaction between 2 units. For instance, now I need to compute the interaction between these 2 big monomers, effective monomers. Okay, because I know all the interactions between all the realistic monomers. So I recompute that, and now I have another problem, which has a less large amount of monomers, but their monomers are bigger. And I know the effective interaction between those larger units. And then I redo the same process. I regroup 3 big monomers into even bigger monomers, and I recompute the interaction, and I end up with another polymer problem. This is the idea of renormalization. And at the end, in some cases, and we hope it is the case here, there will be a convergence to a fixed point. At some point, the interaction and typical sizes of those objects won't change anymore. Okay, so we hope that we will end up with a fixed point, and in that case, the properties become self-similar. Okay, so when we are in this limit, we can compute a lot of interesting things, and in particular, find the statistic of the polymer chain. Okay, this is the idea we want to perform here, and we will go slowly based on the article I sent you. All right, is it okay for the plan? I assume yes. Okay, so let us start. So we'll start with the first part, which is first introducing the type of transformation we have in mind. All right. So we introduce G, which is the number of subunits. So really, I have this. Okay. Up and so on and so forth. And now I will group them. And here in this particular example, G is equal to 3. Okay. Those are my bigger units. Okay, so I introduce, or in fact, G can be anything. I introduce G that is just the only condition I want is that it's a smaller number, a much smaller number than the total number of monomers. Otherwise, it is completely absurd. All right, so the first question is, how many subunits am I creating? Here we see I have 3 subunits, okay? So generally speaking, what is the number of subunits I have in such a renormalization step? Let me call it like that. So what is the number of subunits after one renormalization step? Well, it's the total number of monomers, n, but divided by the number of monomers I put in any of those bags. So n divided by G. n divided by g is the number of bigger units. Okay, is it clear? All right, so I assume it's okay. So I have the number of units, and now I would like to also characterize the size of each renormalized monomer, each new unit. So first of all, let us place ourselves in the case where there is no interaction. I'm starting from an ideal problem, okay? For an ideal problem, what is the size after one renormalization step? Meaning one grouping of monomers into bigger units. Let me call it A1, but in the ideal case, meaning there is no interaction energy. So according to you, what is the size of this bigger unit? Remember, an ideal polymer chain has a self-similar property. No idea? All right. We are just, sorry, yes? I'm sorry, I don't hear you well. There's a problem of microphone? No, sorry. It's probably my headphones, but I don't hear you. So anyway, I will assume that what you meant is that since it's an ideal chain, when I group G units together, well, the size of what I obtain is square root of G times the size of one monomer. And this will be true because we discussed that in the ideal situation. There is this self-similarity. It's a fractal object. So no matter how I group the unit together, I still have this behavior. So to summarize, I have my polymer chain with certain monomers of size A. If I group plenty of monomers, G monomers, together into a bigger unit, well, the size A1, after renormalization in the ideal case, well, is simply square root of GA. That is what I meant, okay? So this is the simple case where there is no interaction. All right. So I know that reference, but the fact is that I'm interested in situations where, in fact, I have positive interactions because I want to be in an ideal, or I mean, a good solvent case where the chain is expanding. Okay, I don't consider the collapsing case where V is negative. We already chatted about that, and there is less interest here. All right, so now when V is positive, what do you think about the size of A1? Let me call it A1 without the zero symbol here. What do you think? How does it compare to the reference when there is no interaction? Okay. It's expected to be bigger. It's expected to be bigger due to the positive repulsive interaction. Well, the chain will swell. It will be larger in size. So you expect to have something like that. All right. And so you might just end up writing it this way without losing any information with a positive increment function, h. Okay. H is a positive function. I don't lose any information. I put all the knowledge I don't have into H for now. All right, so we can still discuss a bit what are the dependencies of H. So according to you, this problem, a priori, will depend on what? So H is a dimensionless function. So it should be a function of dimensionless numbers only. What do we have here as dimensionless numbers? Well, the total number of objects, for instance, n. It's a function of the dimension as well. A priori, let's put all the possibilities. It's a function of the coupling constant in dimensionless fashion. So V, remember, U is V divided by A to the D. So it's a dimensionless number. So I put it directly in a dimensionless form. What else? A priori, the way I group. If I group a lot of units together, perhaps this H will grow as well, okay? And there are no other dimensionless numbers, okay? So a priori, I have listed all the possibilities. What do you think about the dependency in N? We are talking really remember the drawing here, we are talking about the size of the renormalized entity based on the interaction between them and potentially with the close neighbors and the solvent, if any. But if I double the length of the polymer, do I really change the size of that subunit? Do you think there will be a dependency in the total chain length? No. Okay, so we expect that it doesn't depend on the total length. So I will remove that one. And the three other dependencies, they are there, okay? But the real variable here that will be interesting in the renormalization process is this one. This is a parameter. I fix the dimension of space before starting to work. And I also fix my procedure. For instance, I will group the units by 10 or by 100. And it will be my parametric number. So it's a parameter of the problem, but I will rapidly forget the dependencies in G in what follows. Okay, so I can just summarize this by writing, without doing much calculation here, that we expect that the renormalization size of the monomer will be given by square root of G times A, this is this guy, and an increment, something positive and bigger than 1 here, which is 1 plus H, which is a priori a function of U. And I don't write the two other dependencies in D and G, okay? All right, so you don't do anything here when you write that. But still, we have this information with H positive. All right, so let's do the same, not for the size, but now for the energy, the interaction energy. So now we want to do exactly the same. We have V equals 0. So we go back to the ideal reference first. According to you, when I have no interaction between the monomers, so here, those guys don't talk to each other apart from the backbone interaction. Of course, there is a rigid bond between them, but they don't talk to each other with other interactions. Up. Here and here. So V equals 0. There is no interaction between the monomers. Now I group them into larger subunits. Oops, sorry. Wrong tool. And the question is, what is the interaction between the two renormalized units, the two big units? So we call it V1, but in the ideal case. According to you, what it is? The interaction between real monomers is 0. So if I sum all the possible interactions and now calculate the interaction between the renormalized unit, it's also 0. I mean, just by summing zeros, I get 0. So a priori, we have this. We could still think a bit about the limit. What about the limit where V tends to 0, but it's not strictly 0? Okay. So we are just trying to get, previously with A, we were having a finite expression at the zeroth level here. You have a finite expression, it's non-zero on the side. For the interaction energy, however, you have 0. So we might try to find an equivalent instead of that limit. That is why I'm placing myself in the limit where V goes to 0. Do you have an equivalent of V1 naught when V tends to 0? So according to you, how does it depend on G, for instance? It's an interaction number. Typically, what do you expect? How does it go with G? Which power of G does it go?
G squared.
Yes, because it's an interaction parameter. So when I group the units together, I need to count all the possible interaction, all the possible pairs of the problem. So typically, I forgot all prefactors here, but it must go something like G squared multiplied by the rho interaction parameter. And when V goes to 0, we recover the fact that the limit is 0. But this is the equivalent. So I should write it more to avoid the prefactors here, like that. Okay. All right, correct. So it's a G-squared-like dependency. Perfect. So now let us continue and ask for finite interaction case now. Now V is a finite number, it's positive. And so what do you think about the real renormalized interaction volume, like the excluded volume, for this case? Will it be smaller or bigger than this quantity? What is the relation between the two in terms of inequality? I'm grouping units together to form bigger units, okay? And I'm asking the question, if I have a finite interaction now, okay, is the renormalized interaction larger or smaller than in this reference case, ideal case? What is the effect of the interaction, in fact? Take two monomers, ideal situation, and then you branch the interaction. They will tend to separate. This is what we discussed already here in the fact that, for instance, the size of the rescaled unit is larger than the unit when there is no interaction. Okay, so there is a rescaling. H was positive here to express the fact that we grow in size. Okay, so if we grow in size, we also decrease the interaction. The interaction is the strongest when you are very close, but as soon as you are swelling, you reduce the interaction. So we expect that V1 is something which is smaller than the reference in the ideal case. Okay, so for the same reason as previously, we can just write V1 as a reference value, and then without losing any information, we just remove something to 1, where L is a function that is in between 0 and 1. So that we express the fact that the energy interaction is reduced. All right, so this is for the volume. It's exactly what we had done for the size. And now we would like to discuss the dimensionless number, which is, in fact, the U quantity. So I remember that, I remind you that the U coupling constant, which is a dimensionless coupling constant, is simply defined by the difference, the ratio, sorry, between the excluded volume and the monomeric volume. It's a definition. So at order 1, meaning at the first step of renormalization, of grouping the units together, U1 is simply defined the same way. It will be V1 divided by A1 to the D, just by definition. And so since we now uncovered typical expressions for V1 and A1, we can just plug them inside this relation. And so we end up with V10 1 minus L over A1 was square root of G A 1 plus H, everything to the power D. And V10, remember, is G squared times V. Okay, as we explained before. So I can also plug that here, and I end up with G squared V 1 minus L over 1 plus H to the power D. And here I have GD over 2 AD. So stated differently, I end up with a power law, 2 minus D over 2, times V over AD is defined as U, as you can see from that line. So it's U. And then I have a function, 1 minus L over 1 plus H to the D. Okay? So now we know that H is always a positive number or function. L is always positive and smaller than 1. So what do you think about that ratio? No matter the values of L and H, can you provide bounds? So it's reasonably positive because L is always smaller than 1 and H is a positive function. So this is positive. And in the worst case, L will be equal to 1, and this might be 0, okay? So in fact, I can rewrite this the following way. Just to have the same kind of function as before, Ku, where K is a function that is between 1 and 0. Okay, so I can always write things this way. And let me just summarize. We found this expression. Okay, so the new coupling constant after one step of renormalization is the rho coupling constant. And then there is a dependency in how I normalize in the dimension and in the coupling constant itself. Okay?
Sorry?
Yes, please.
Yeah. Why the fact that there are interactions makes the size of the subunits change?
So remember the tutorial number 3, for instance. Okay? Let me take a new whiteboard here. Remember the last tutorial. What we did is that first, when we have no interaction, V is equal to 0, we had a chain whose typical extent, R, was going like the size of a monomer n 1/2. This is even tutorial number 1. Okay, in last tutorial, what we did is to say, okay, now we are branching interaction between the object, and we are saying that this interaction is given by V, which is positive. In that case, remember, we ended up with a swollen exponent. It was like in 3D, it was, or let me give it in general, it was d plus 2, 3 over d plus 2. That was the Flory exponent. So nu in 3D is equal to 3 over 5, which is bigger than 1/2. Meaning that now your chain, and n is a very large number, so your chain is much larger. So it's exactly the same. Since we are talking about large numbers, we have this scaling analysis. Okay?
Okay. Okay.
All right, so this is, your question was about, I think this equation, showing why H is positive. Okay? Why the size is larger than the reference when there is no interaction. Okay. Okay, let me go here. So now we've identified the coupling constant, and of course you can easily find K by saying that 1 minus K is equal to 1 minus L over 1 plus H to the D. So there is a relation between K and L and H. Okay, you can find it easily. Okay, so let me start with now the second part. So in the first part, what we did is to introduce the main operation, basically starting with a certain number of units and then grouping them once and finding some relation between the previous state and the renormalized state. What we want to do now is to do that p times, like repeat the process, regroup the units and then regroup them and then regroup them, and to see what happens when there is a fixed point in particular. So this is what we would like to do. So now we will iterate the process. So we will introduce P renormalization step. And so after P renormalization steps, you started with a problem which was defined by the size A of the monomer and the interaction between two monomers, or at least the coupling constant of the problem. And after P step, well, you end up at AP UP. So what we did just before was A1 U1, okay? P equal 1. So that's what we want to do now. So I have a simple question. Do you see a critical dimension, D, DC, we would call it, appearing in the problem? Remember this expression here. If I look at what's going on at the bottom, can you see it here? what do you see? There is a power law in the G step. So is there a particular value for D without any calculation, just by watching this formula?
It's 4.
Yes. So precisely 4, we can, without any calculation, say that there seems to be a threshold value, DC equals 4. Remember, this is what we identified last time. Based on this formula of Flory here, we saw that when D is equal to DC equal 4, you ended up with nu is equal to 1/2, despite the fact that we had interactions. This is not a V, and this is a nu. This is the exponent that is here. So there seemed to be a dimension of space for which you would recover some ideal behavior. Okay, well, we have it here as well. DC equal 4 appears immediately. UP is equal to, as you can see here, G to the 2 minus D over 2. The coupling constant at the previous step, so it was U towards U1, but now it's UP minus 1, the previous step. And there you have 1 minus K, which was a function of U at the previous step. Okay, this is what we had. But UP minus 1 is itself obtained by the same kind of power law. So there is a factor 2, a power 2, UP minus 2 here. Sorry for the typo. Up. UP minus 2. And then 1 minus K, UP minus 2, 1 minus K, evaluated at UP minus 1. Okay? And so on and so forth. So that at some point you end up with, as you can immediately see, a P. U0 is in fact U. Let me just introduce this definition, but it's obvious. It's prior to any renormalization, so it's the raw coupling constant. And then you have this product for J going from, let's see after, of 1 minus K Uj. Okay? So you will stop here at when 2 is equal to P, so you go from 0 to P minus 1, right? Okay. So you see, we have a product of numbers that are all smaller than 1 and larger than 0, basically. You factorize all of them, so the product is still smaller than 1. And the more you increase the number of objects, well, the more you decrease this factor. But at the same time, you have here, well, this is a constant number, but here you have something which might be growing. In particular, when D, the dimension of space, is smaller than DC, this might explode. So you have something which is growing with P and something which is decreasing with P. And so there might be a limit, there might be someone winning, we don't know. But for sure, what we know is that if D is larger or equal to DC, well, this factor will now start to decrease as I increase P. So for sure, the total product will decrease. Therefore, UP, when P goes to infinity, will tend to 0. Meaning that above the critical dimension of space, which is equal to 4, after a sufficient number of iteration, of grouping iteration, you will kill the interaction. Is there a question? No. Right. There was a problem of microphone here. So I hear myself. Could you cut all your microphones? Could you mute yourself all? Okay, let me try. Is it better? Yes, perfect. There is no more echo. All right, so we identified a dimension of space, and now we would like to look at what happens at the P level. So let me now go to question 2, and I would like to provide all the expressions. So first of all, how many subunits do we have at the P stage? I'm grouping n times P times the subunit. So what is the remaining number of subunits? It's n divided
over JP.
Yes, correct. When P was 1, just for the first step, we said that, well, now we have only n over G units. But now we are regrouping them another time, so it's n over G squared, and then another time n over G cubed, and to the power P for the P grouping, okay? So this is the number of units that are remaining in your polymer system at the P step. Now you have kind of renormalized polymer chain with very big units, and in fact, inside you have a lot of subunits, but you don't look at them anymore. So you have a less number of big objects, okay? All right, okay, so now we would like to provide the recursive relation. And just before that, how G and P should be chosen to make sure we still are relevant in terms of statistics, according to you, thanks to that expression. What do we want for that number?
We want that number to be kind of big too.
Yes, you're correct. Otherwise, if we end up with one big monomer, well, it's become a sphere problem and there is no statistics anymore, okay? So we still want to have a large number of big blobs or big spheres, okay? So it places a condition, but which is kind of easy to fulfill because we are always in the limit where capital N tends to infinity, so it's okay. But in practical situations, we want to be in this situation. And typically you can, I mean, you can choose whatever you want for G. It should be a finite number. So you can take this like 3 and you can take like, don't know, 4 typical rescaling steps. And in practice for polymer problems, after 4, 5, or 6 regrouping units, you end up on the fixed point. So I'm just providing you this for you. So you see it provides something like bigger than 100, which is easily fulfilled, okay? So in practice, there won't be any problem for polymer problems, but there you have to trust me. All right. Okay, so now let's attack the recursive relations between 2 steps. So let us start with the size. So A at the P+1 level, how does it go with A at the P level? So this is the size of the unit. To help you, I can show you.
It's only multiplying by square root of G.
Yes. So you have this square root of G. It's here. Sorry. Here, this square root of G, the A at the previous level, and then this rescaling function. So you're right. It scales like square root of G and the previous proposal at the previous step, and then you multiply this by 1 plus H, same function, at evaluated at U. Again, I hear echoes. So if you have microphones that are on, please cut them. Okay, so this is based on the fact that we assume that this is the same function. I'm sorry, I have problems with my earphones. Do you hear echoes when I?
Yes.
Yes. So there is a problem. Sorry?
I think it's the Condorcet rooms.
Or can you cut the microphone or in the Condorcet room? It's okay? Yes. I think it's better now. Thanks. If you want to just ask a question, please just stand up and come and click on your unmute button. Thanks. Sorry for that. All right. So here, of course, we have assumed that H is the same function, but of course, what we did so far by introducing this renormalization story, we started with the realistic monomers. You remember it was A instead of AP here. But in fact, whatever the initial problem is, it's the same story. I could have started already with a renormalized chain if I want. I know that size, I know the interaction, it's UP. So it's exactly the same function that is here. That is important. Let us look at now the energy aspect and not the size. Well, but exactly with what you propose, we can just copy paste this relation that is here. So it's G to the power 2 minus D over 2 multiplied by a function of the previous step. Okay. So it's G to the power 2 minus D over 2. The coupling constant at the previous step, and there was this prefactor, which was 1 minus K UP. And again, the function K is the same as the one we discussed before for the same reasons. So those are my iterative relations between step P and step P plus 1. Okay. All right. Now comes the story about the fixed point. Assumption. We don't demonstrate that. This should be recovered when you do the actual calculation of K and H. We will discuss that at the end, and they have been performed, those calculations. But here we assume that there is a fixed point. Fixed point means that when P goes to infinity, UP tends, the coupling constant, tends to a constant value. At some point, you can group more and more the unit. It doesn't change anymore. You have reached a plateau, and the interaction energy is the same. Okay, this is a fixed point. So this fixed point means that the U tend to a constant value. So now you can use the iterative relation and write that AP plus 1 over AP using the first one, which is always equal to J1 plus H evaluated at UP, when P tends to infinity, should tend to a constant as well, because now UP is fixed to U star. And so it's a constant, and we call that mu. So the coupling constant tends to a constant. The ratio between the size at the P plus 1 level and at the P level tends to a constant. Of course, the size is not saturating, because if I group units, well, I increase the size. I have 3 small units, I group them together, it's bigger, okay? Even in the ideal case. So this doesn't saturate. What saturates is the ratio, the function, I mean, the way it grows when you group them. This is saturating to a constant number that is mu, okay? And remember that UP is in fact equal to the excluded volume divided by the monomeric volume to the power dimension. So if UP tends to U star, it means this tends to U star, constant. And thus, it means that VP tends to AP to the D when P goes to infinity. So the excluded volume tends to the art sphere volume of a monomer. So in the scaling regime, in the fixed point regime, you end up with the fact that, I mean, all the big renormalized units, they behave as art spheres. Now you have a paving of the space with art spheres. Okay, so it's a rigid-like behavior that appears. So it's a consequence of what we just said before. Okay, so now I would like to identify what is the relation that provides U star. Well, in fact, we could re-express those two, but in the fixed point regime. So this one, AP plus 1 divided by AP will tend to mu. So I have mu is equal to square root of G, thanks to this guy, and 1 plus H evaluated at U star. Okay, and the second equation says that this guy tends to U star, but on the other side, this guy tends to U star as well. So they will cancel if they are non-zero. So I end up with 1 is equal to G2 minus D over 2, thanks to that guy. And then the correction factor evaluated at U star, 1 minus k u star. If u star is non-zero, of course. If it's 0, we already discussed that when the dimension of space is bigger or equal to 4, then we tend to a coupling constant that vanishes and we recover the ideal case. So we know how to treat the ideal case. We don't really need it to do now. So we assume that u star is not 0 here. Okay, the fixed point is not 0. Is it clear? Assume yes. So now we have two equations, and there is one of them which defines u star. In fact, if I have calculated k, and this will be discussed later, but let's assume I have calculated k, I know g, this is my choice, my way of grouping units. I know the dimension of space. So if, at least numerically, I can find the value of u star from this equation. And if I find u star, I can then branch it into the equation above. I know h, I will explain how after. I know g, so I can find mu. Okay, so this is how I can find the fixed point properties. All right. So now let us move on and look for scaling laws. So do you have questions on that? No? Seems clear? All right, so now we would like to look at for a scaling law about the chain size. So now I forget about this renormalization process for a moment. I have this chain who has a certain extent capital R. And the question is, what are the dependencies of R a priori in the initial problem, the real polymer problem? So can you list all the values, all the variables? Any proposals are welcome. What should R depend on?
I think it would depend linearly on A.
So there is A, yeah.
And the dimension and on the total number of numbers.
Only?
And the excluded the U.
Yes.
U
A priori, the interaction is important to define the scaling of R. Yes. So either I put V, the real excluded volume parameter, or I just put U, the normalized one. There is no problem because in any case, the other variables D and A appear here, so they are already listed. So this is equivalent. Okay. So how many variables do I have? I have 5 quantities here. And I have 1 unit because you see, this is a size, and this is a length scale. This is also a length scale. And those guys, the 3 of them, they are dimensionless. So in fact, I have 5 units, 5 variables, minus 1 unit. So I end up with 4 dimensionless groups that are relevant. I guess you are all familiar with the pi theorem or the Buckingham theorem for scaling analysis, okay? So as you correctly pointed out, we have no choice but R being proportional to A. So this is 1 dimensionless group. This is the only way to non-dimensionalize R. And this should be a function of the 3 remaining dimensionless groups or numbers, okay? This is very broad. And again, here I have the dimension, which is actually a parameter, so I could also forget. It's not independent on the dimension, but I assume it's a parameter, so it doesn't change in my problem. When I group the units afterwards in the renormalization process, I don't change the dimension of space for now. However, I change the energy of interaction, and I change the total number of units because I'm reducing the number of units by grouping them. So I would keep at least those 2 dependencies. That will be useful. Okay. So I didn't do anything very deep here. I just say that, well, all my unknown questions are put in F. But generally speaking, I have linearity with A and the function of size and interaction. All right. So this is trivial, but what we would like to do is to do that now at the P step, and eventually in the fixed point limit. So this is what is going on now. So I could really have said things in a similar fashion than saying that now instead of having this real polymer chain, well, in fact, let me forget. I have now a polymer problem with monomers that have a certain size AP, whose total number is, let me remember, the notation was that, I guess, N over JP. I have a certain number of objects. And I was branching some interaction, for instance, between this guy and this guy, that was renormalized. So now it's a UP interaction. It's not U, but okay. But just if I draw it like this, well, it's another polymer problem. It's really equivalent to that. And of course, another important comment is that the typical size of this guy is R. And sorry if it's not to scale, but the typical size is also R. No matter the way I group things, but the size, the total size is the same. So this says that I can really exactly use the same formula that is provided here, but by replacing A by AP and U and N by the proper values. Okay, so without any cheating here, I can simply say that, well, I have another expression for R. R is equal to AP and F N over G to the P and U to the P11. And the crucial aspect here, it's like before, is that this function is really the same as before. It's the same F. It's not another function, okay? Because it's exactly the same problem. I just changed the name of what I call a monomer size and a number and an interaction. Okay? Good. So I have the same scaling expression, if you wish, or at least dimensionless expression. And it is also true that I can do that at the P+1 level, in fact. I can just, it's obvious, but I just write it. Same function. Careful, the number has been reduced at the next level and the interaction energy is different. Okay, and I could do that for any P. But I specifically chose those because now I identify the ratio between AP+1 and AP, and I remember that in the fixed point limit, this ratio will tend to a constant that is mu, so that is why I need those two. Okay. Any question on that? No? All right, so let us go on. Now we would like to prove the existence of a power law. So we would like to place ourselves in the scale invariant limit. Scale invariant is the same as fixed point. Huh? It's equivalent. Okay, we want to be in that regime where the properties become self-similar. I mean, the energy doesn't change anymore, and the rescaling of the size is obvious. It's trivial. It's a hard sphere packing. So we place ourselves in this fixed point, and we would like to see, can we prove the existence of a certain power law between the size and the number of objects. Okay, so let's retake the previous expressions that are here. And now we will take the ratio of the two. So the ratio of the two says that 1 is equal to AP+1 over AP, which is mu, or 1 over mu. I will take the top divided by below, so 1 over mu. And then I have a ratio between F, evaluated at N over JP UP, and same F divided by N over JP plus 1, UP plus 1. Okay, so stated differently, I don't consider the mu equals 0 situations here again. So sorry, what did I write here? What I wrote is wrong. Be careful. Excuse me for that. I was already placing myself in the scaling limit, but I'm not in the scaling limit for now. So I will just erase that and write first the proper expression. Okay. So AP plus 1. Now I'm at step P and there is no fixed point. And now I take the limit where P tends to infinity when I reach the fixed point. So in the fixed point limit, now I get 1. This becomes 1 is equal to 1 over mu. F in the large P limit, and then U star, because the coupling constant has saturated. Sorry, it was JP here. Okay, and this is also U star. Okay, of course P is large here, huh? There is no more P, but okay, you understand what I mean. And I can, if you prefer, introduce this definition. It's an X function, okay? So I end up with mu is equal to f of gx divided by f over x U star. And stated differently, I can remove the U star, it's a constant, so I just say. Okay, so it's equivalent to saying that thanks to the last line here, this guy divided by this guy is equal to mu. All right, so it's just a writing process, but I have this function. So what can I do? I can do two things, and I think you already did that several times. We recognize here, if we derive it with respect to G, for instance, if I derive with respect to G, I will have X that goes out. And here I have F. So I will have F prime X equals to F. So you remember Euler's problem here. We end up with an homogeneous polynomial, okay? Polynomial. So let me derive it with respect to J. So I get, and is equal to mu prime of J, F of X. And I can now take the expression when G equals to 1. So I end up with X F prime X is equal to mu prime of 1, say, F of X. And I can just provide a name to this object, mu. Mu is simply mu prime evaluated at G equal 1. G equal 1 is really grouping the unit by 1, so it's non-grouping the unit. All right, so X F prime of X is equal to a number times F of X. So what is the solution of that for capital F? I already gave the solution. What do we recognize? So you derive the object and you multiply it by X and you recover the object. So the solution is something like that. It's clear that F prime is equal to nu A X, nu minus 1. So if I multiply it by X, I recover nu times A times X to the power nu. All right, so that is an interesting aspect. I get a power law. I get a polynomial. Okay, so now I can plug that back here first. You know, f gx over fx. So mu is equal to f of gx over fx. F being a polynomial, that is a the object gx, the variable, sorry, to the power nu. And here it's a x to the power nu. So plenty of things cancel out and you end up with g nu. So mu is connected to nu by this relation. And remember, we had said that mu prime is nu g nu minus 1, and mu prime of 1 when g equals 1 is nu. So we really end up with our definition. So this is the important relation. Nu is not something that is unknown, it's related to mu and g. But I can do more than that. In fact, if I go more towards this situation here, here, R is equal to AP times F. So R is AP times F of what? Of ng to the p in the scaling limit. So F of, which is AP A n to the g divided by g to the p, sorry, to the power nu. So I end up with this relation A and nu, and here I have something which is g to the p nu or g nu to the p. And g nu is mu. Look at this expression. So I can just rewrite things this way. Divided by mu to the power p. Okay. That's one part, but I'm not done yet. So I assume that, of course, at near p equals 0, so at the beginning of the renormalization process, there is no fixed point. I'm not yet in the fixed point. However, after a few renormalization steps, I will enter the fixed point, and then forever I'm in the fixed point regime. That's the definition. So when p goes to infinity, most of the operations will be in the fixed point regime. So I can really say that basically AP is what is mu times AP minus 1. Remember the definition of mu, which was provided here. AP plus 1 over AP tends to mu in the fixed point. So it's pretty clear that I have this connection between AP and AP minus 1 in the scaling regime, which is also mu to the power 2A P minus 2, provided that P is large. And again, mu 3 A P minus 3. And neglecting the details about the starting of the problem, it's close to be mu P A0, that is A. Of course, I do a little mistake here, okay, but it's just a correction factor. So basically, I end up with the fact that this is mu, sorry, it's not the good line. Up. This is close to be A n nu, mu P divided by mu P. And there is A missing. And so it's A times n nu times A, where A is a constant. Remember, it was identified here as the prefactor of the polynomial. So it's a constant number. So just in terms of scaling, I end up with A n nu. And this is R. So we end up with the interesting fact that in the fixed point limit, you demonstrate, if there is a fixed point, you demonstrate the existence of a power law, a scaling regime between the size of the polymer chain and the number of objects. Okay. Any question on that? Okay. Good. Can we do more than saying that? Can you identify nu? So we say that mu is g to the nu, right? So I can take the log of that. Which leads to nu is defined as simply the ratio between the log of mu, constant that I've been able to identify in the fixed point limit, and the log of g, and g is my parameter, how I group units, 4 by 4, for instance. So I know g, I'm deciding what is g. So I can find this exponent from the procedure. So let me explain the procedure again. So the renormalization ID, very generally. So first of all, I have a certain problem. Certain problem which is in fact made of monomers that can interact with a certain energy. In dimensionless unit, it's U, and with a system and monomers that have a size A, and I have a total number of objects which is very large. This is my initial problem. And what I will first do is to look at the function when I group units together. So I will group units together. This will have a renormalized size A1. And as there was an interaction between the two, now there will be an interaction that is called U1 between the two bigger subunits. And this needs to be done by a proper calculation, meaning really, I group the units by a certain number G together. And I know between units what is the interaction, so I can compute all the interactions with the G squared pairs. Same between all the objects in this bed and in this bed. Okay, I can do that. And then I can compute, and this is a mathematical problem. I have to do it. I didn't do it yet. I'm just showing you the principle. So I need to compute U1. So A1 and U1 need to be computed mathematically. But as soon as I'm able to do that, it means that I have identified the following function, K, and it was H, I guess. Remember the initial problem? I was saying that when I group the units together, there exists a function. I don't know it yet, but I should calculate it. There is a function for the size, and there is also a function for the energy. It was K. U1 was rescaled thanks to K. So I need to do that. But assume I've done that. First step is to calculate them. Okay, first I fix G. I'm the one who is doing the renormalization. I decide to group them, let's say 5 by 5. So G is equal to 4. Then after this grouping, I calculate the function that allow me to know the problem at the first renormalized step. So I know K and H. And then I go to the expression providing the fixed points that are here. So now I know this guy. I know this guy because I just explained that I calculated them for one grouping. I know this guy because I know how I fixed G. It was 5 in my example, and I know the dimension. Okay? So from this relation, I find U star by inversion. So I find U star, then I plug U star here. So I know everything apart from mu. So now I find mu. And finally, I know everything I need. Since I know mu and G, I find the exponent. This is the renormalization strategy for a polymer. So calculate KH, then calculate U star, then mu, and then nu. All right? That's the main idea. Now we want to put that in practice. And we will do a development near the fourth dimension, with epsilon being a very small number. So really we work at the critical dimension where everything is ideal, and then we reduce slightly the dimension so that we start to put in some interaction energy again, and we do a Taylor expansion in the dimension, as weird as it might sound. Okay, but we do it mathematically, so there is no problem. All right. So interestingly, the paper I was mentioning to you by Gabet and Garel. So let me just change my screen and go back to the PDF. Ah no, I don't have the PDF. Okay, anyway, you have the article by Gabet and Garel. So in this article, what they do is exactly that. They calculate. I mean, they set a problem of polymers. They branch some interaction between the monomers, and they calculate really those quantities. They did that for us, and they provide them as expansion. So here they tell us that very near the critical dimension, they do that under some assumptions. So I encourage you to read the article, but they are able to really find an expression for H and K. And we won't have time to do it, but please have a look. All right, so let us use their result and see what we can learn from that. So just generally, without looking at their result, when epsilon is going to 0, what do we expect for all the quantities? Let us start by K. So K is defined as in the proper one is this one. Here. So when look at this equation, the one saying that 1 is equal to G2 minus D over 2. I can rewrite it on our screen here. 1 in the fixed point limit is given by G2 minus D over 2 in factor of 1 minus K of U star. Now we are taking the limit epsilon tends to 0. So remember, J2 minus D is 4 minus epsilon divided by 2. And this is, for this one, we'll cancel with this one. And you have J to the power epsilon over 2 here. So when epsilon goes to 0, you end up with 1 is equal to 1 minus K U star. This says that K tends to 0 when epsilon goes to 0. All right. So K goes to 0. Remember what was K? We have said previously that 1 minus K is equal to 1 minus L over 1 plus H to the D. This was how we introduced the scales in energy. It's here. Here. You have the energy at the first level is the energy at the 0th level in dimensionless unit, a function of G and 1 minus K. And K is really given by L and H by this relation. 1 minus K is 1 minus L over 1 plus H to the D. So this is what I'm using here. 1 minus K is 1 minus L divided by 1 plus H to the D. So if now K goes to 0, it means this quantity goes to 1. Remember, L is in between 0 and 1, and H is strictly positive. So what do we get for L and H? Any idea? K is going to 0, so the only possibility is that L goes to 0 here and H goes to 0, so that the ratio goes to 1. Otherwise, the ratio is smaller than 1. So it implies that both L and H go to 0. All right, so K, L, H goes to 0. So K, H goes to 0 in particular. And so what about U star and nu? What about nu? Remember the expression of nu. Nu is given by the log of mu divided by the log of G, we said. And mu is what? We know the expression of mu. Mu is provided somewhere here is one example, but I will need another one. Yeah, mu is provided by square root of G 1 plus H. So nu is equal to log square root of G over log G plus log of 1 plus H Okay, and so this is, the first is 1/2 plus this function. I should have commented on that earlier. In fact, it says that, you know, h is a function that is necessarily positive. So this number is always positive, whatever the choice of g and whatever the values I have here. And therefore, it says that in all cases, nu is bigger than 1/2. So the exponent, when you have interaction, is always bigger than the ideal exponent. Good. But here now we are saying that h is going to 0. So this will go to 0 here, and I have log of 1, so it's 0. So it says that when epsilon goes to 0, nu tends to 1/2. So in the critical dimension, we end up with an exponent that is 1/2. It's obvious to you because you know that when there is no interaction, the exponent is 1/2. You did that calculation at tutorial number 1. But here we didn't do anything. We just said there is a critical dimension where the interaction vanishes. That's all. But we didn't know the 1/2 in a sense. Well, we demonstrated that nu is equal to 1/2. So when there is no interaction, the exponent is necessarily 1/2 by the scaling considerations I've given you here. I gave you here. All right. So now let us use the result near epsilon equals 0 by Garel and Gabe. So the one I provided you before. Those are asymptotic expressions. I mean, and there is some work behind the calculation of those, as you will see in the article when you read it. Okay. Okay, so now we would like to find U star from those. So what should you do if you understood the process? How to calculate U star? Which equation provides you U star? Let me come back. Remember the procedure. I fix G, the way I group subunits, the number of subunits in a larger one. Then I calculate K and H. Luckily, some people did that for me, and they found in particular K and H, and then I am able to find U star. So I'm really invoking this equation. Here, you see, now I know everything because I know K from Gabe and Garel. I know everything that is here, so I can find U star. Okay, so let us rewrite this equation. 1 is equal to G to the power 2 minus D over 2. And we say that it is 1 minus K of U star. The good thing is that I know K of U star because it's here now. So this is G to the power D minus D, so it's again 4 minus epsilon. 1 minus 32 pi squared epsilon U star. All right. So I can just recast this into this expression is a G to the power epsilon over 2, and then this other function of epsilon. And I can also transform that into an exponential. So this is exponential epsilon over 2 log of G. So this provides me, if I put this exponential on the other side, it's exponential minus epsilon over 2 log G should be equal to 1 minus 32 pi squared epsilon at small epsilon. Okay? Well, if epsilon is small, and since G is a finite number, typically 4, 5, whatever, this argument will go to 0. So I can also Taylor expand the exponential, and I will have 1 minus a function linear in epsilon. So I can really identify the two terms. So it says that 1 minus epsilon over 2 times log of g is equivalent, or sorry, is equal to 1 minus 32 pi squared over epsilon. Pi squared was at the bottom, okay, and u star. Which allows me to get the dominant expansion for u star, which is pi squared epsilon squared divided by 64 and times the Neperian logarithm of g. So sorry, in previous tutorials, I was coding this guy, I was really identifying to this notation. So you should keep the log everywhere, apart from France, where everyone uses log Neperian. But the notation is log, log for the Neperian logarithm, otherwise. All right, so we ended up with this, and it's interesting because you know it's a epsilon square behavior. And if you remember the Garret and Gabel expressions here, you see it goes with 1 over epsilon in front, so it's still going to, we really recover the fact that h and k as properly going to 0. So we really have u star goes to 0 when epsilon goes to 0, k and h go to 0 as well. So we are really in self-consistent, we are really self-consistent with ourselves. All right, now we found u star, epsilon squared, and this proper expression. So what should we do now in the program of the renormalization method? What is the remaining step? I want to find the exponent between the size of the polymer chain and the number of objects. First, in the fixed point limit, I was able, using the help of a certain article, to calculate u star, which is the renormalized coupling constant. I have an expression for it. So now in the program, remember, now I'm here. I found the coupling constant, so I should find mu from it. So mu is provided by the top equation. Mu is connected to u star by this equation. So let us go. Mu is square root of g. So this is third part. Mu is equal to this quantity. But what is good is that I know h star from Gabet and Garel. So h star was provided here. It's 4 pi squared epsilon u star. And it's an approximate expression here because I'm near epsilon equals 0. And another approximation is the following: 1 plus 4 divided by pi squared epsilon. And I multiply the u star here that is provided above. So pi squared epsilon squared 64 log of g. Okay, so I have things that cancel out. Sorry, not only the exponent. Pi squared. And so I can recast this into the following form: square root of g 1 plus 1 over 16 log of g. So epsilon over 16 log g. Great. Okay, so we have mu. And finally, in the process we are discussing, when we have mu, we end up with nu using this expression. Nu is equal to log of mu over log g. So I should go back here. Let me use that space. Which is log of square root of g 1 plus epsilon over 16 log g divided by log g. So I can now separate the two terms. The log of the product is the sum of the logs. And again, I'm near epsilon equals 0, and I'm doing, those are approximate symbols, in fact. Everywhere, I should put an approximate symbol. So mu is approximately given by, look, the first one is 1/2. Sorry, mu. Typo, excuse me for that. This is a nu, it's the exponent I'm looking for. 1/2 plus what? Let me Taylor expand. I have the first order term is epsilon over 16 times log g divided by log g, so plus epsilon over 16. So stated differently, this is 1/2 with 1 plus epsilon over 8. Okay. So I found an expression for epsilon. Epsilon for nu, nu of epsilon. So I found the expression for nu of epsilon. And so I can now evaluate, extrapolate this expression. Of course, this will be a source of error because I'm using a low epsilon expression to extrapolate it to the value where epsilon is equal to 1 because I want to go back to the 3-dimensional world from the 4th-dimensional world. So nu of 1 is equal to 1/2 multiplied by 9 over 8, which is 9 over 16. And if you compute that, it's close to what we want, I guess. So it's 6 and something. You can compute it, but it's not so far from the Flory exponent, 3/5. It's a bit smaller, but it's not so far. The reason for that is because we were only calculating the coupling constant at order 2 in epsilon. So if we are able to do the calculation at order 3, we will refine the result, and you can do that at order 4 and so on. Of course, it becomes increasingly difficult, but the strategy is the following. And that is what is typically done in renormalization near a critical dimension. Okay, so I think you understood, I mean, you have all the ingredients to understand and revisit this tutorial that explains what is the method of renormalization. The only thing that we didn't perform here is to calculate precisely the functions h and k. Those functions k and h, they were provided by Gabet and Garel. And this is a very technical aspect now. So I would encourage you to read the paper by those two persons and see how they obtain those functions, but it will take some time. Okay, so please digest that. And the main thing I would like you to remember is the general method of renormalization applied to the polymer chains, and the results that in dimension 4, it's an ideal problem. And then by moving back to 3rd dimension, we are able to calculate an exponent that is larger than 1/2 and that is close to the Flory exponent that we already discussed. Okay, so that you have now another technique in your toolbox when you will attack your thesis and your research. All right, so I think we are done for today. Is there any question on what we did?
Yes.
Yes.
Do you hear me?
Yes, correctly, yes.
Okay, so I just have a question about the beginning of the tutorial. So it's the question 4, so 1-4.
Okay.
Why is V1 0 smaller than V1? No, V1 smaller than V1 0?
Oh yes, it comes back to a question by one of your colleagues. Let me see if I kept the answer somewhere. Yes. So I think the question by your colleague was on the size, and you're on the energy.
Yes.
Your colleague asked why, when I couple, I mean, I group the units into larger units, why the size is going larger than in the ideal case. Okay, why? I mean, why the size is larger than square root of the number of objects I'm saying. This is coming from the fact that the interaction energy repel the monomers from each other. Okay, now let's talk about the energy. It's the same idea. you don't have energy in the problem. So your chain is allowed to really cross itself, and you don't have interactions between the. Now, if you branch interaction energy between these monomers, the monomers will start to repel each other and go further away. So on a typical average configuration, the monomers are typically more separated than what they would do in the ideal case.
Okay, yeah.
The interaction energy we are putting here, the excluded volume parameter, we have to remember that this is not only the hard sphere repulsion. If you remember the previous tutorial, in this U or V, there is also the effect of the solvent with the van der Waals interaction. Remember that?
Yes.
Yes. So it means that now you're separating the monomers when you branch an interaction. So if you separate the monomers, well, the van der Waals interactions are also diminishing.
Okay.
Because this is coming from interactions. So on average, if your monomers were very far away, you would not have any more interaction, either repulsive barrier, but also attractive van der Waals interaction. Okay? So in a sense, if you are agreed that you're separating the objects more when you put interactions, well, on an average typical realization of your random process, you will have an energy of interaction which is smaller.
Okay, I understand.
This is the idea. But of course, you could also disagree and just say, where is it? Sorry, I just need to find the proper slide. I think it's this one. You could also just stop here. This is okay, you agree it's the reference, and then it's 1 minus a function. And you should, for now, perhaps avoid that. You should just say, okay, I don't buy that, and I try to work with that. Anyway, I put all the, let's say, under the carpet, in everything in L. So, okay? So I have the right to write this equation is still valid in a sense.
Yeah, sure.
Okay, but you understand the physical arguments behind.
Yeah. Okay, I see. Okay. Thank you.
Okay. Any more question? All right. So if not, we will stop here. Again, thank you. I have the impression that it was a bit difficult to follow, thanks to the weaker interactions with respect to last time. So please digest it. Go back to the video I will put online today, and then come back to me with questions by private emails, for instance, and then we can chat. Okay? So I wish you a wonderful weekend, and we see you next week. Bye-bye.